Let me add a page in here. Hold up. So yeah, let's wrap up. Trying to turn this page. Let's wrap up the substitution and elimination. I have this in the handout, and it just wraps up the different types of reactions. So for SN2, that's favored in polar aprotic solvents. The rate is second order substrate nucleophile. The preferred substrate is a primary. And one of the things that's notable is that when that reaction happens, there's inversion of stereochemistry, right? Because the nucleophile comes in and attacks from the opposite side of where the leaving group is leaving from. For SN1, the solvent is protic, polar protic. It's a first order rate law, first order in substrate. So the nucleophile does not affect the rate. Preferred substrate is tertiary. And if you react, if an SN1 reaction happens on a chiral center, the products are going to be racemic, right? So you're going to get both products. And that's because when it goes through the carbocation intermediate, there is no preference for how the nucleophile comes in once the carbocation is formed. All right, so for E2, that's again, that follows kind of the same path as SN2, prefers a aprotic, polar aprotic solvent. It's a second order rate law, first order in substrate, first order in base. This is what differentiates the E2 elimination from SN2 substitution, and it is the presence of a base. Bases and nucleophiles are not the same, right? Bases are proton acceptors, nucleophiles react with electrophiles. And even though a proton can be considered an electrophile, it's a specific type, right? Bases prefer protons. They don't prefer to react with other electrophiles, right? Also with the E2, he prefers tertiary substrates because the products are more stabilized because you get a more substituted alkene from a tertiary substrate. All right, so, and then all these other special considerations, you need a strong base, and the relationship between the alpha proton and the leaving group, excuse me, has to be anti-periplanar. All right, it's anti-periplanar. And then for E1, right, protic solvents, just like the SN1, it's a first order rate law, just like the SN1, prefers tertiary substrates like the SN1. The only difference is once you get to the carbocation, you do elimination instead of substitution. And we talked about the fact that the conjugate base, that's what the E1CB indicates. Right, the conjugate base can come in and do the elimination step. It can be the conjugate base, or it can be the leaving group, which in some cases may be water, some cases it may be something else. All right, so the conjugate base or leaving group. Can do the proton transfer in the elimination step. All right. All right. Any questions about anything related to elimination or substitution? All right, so the next topic that we're going to study is conjugation. Right, conjugation is a specific circumstance where you have And if you watch the video, this is just kind of a recap, right? Where you have and this is the most simple conjugated molecule. This is 1,3-butadiene, right? And if you notice, and this is the easiest way to think about this, is that there's a pattern, right? There's pi, there's a sigma bond, and another pi bond. So pi, sigma, pi. All right. So that is the basic definition of conjugation is what? Somebody help me. Somebody who watched the video that was sent or read that section in the book or watched another video or whatever, help me out with that. What's the basic definition of conjugation? Anybody? All right. So let's move on to another part of the discussion. All right. So when you have conjugation, when that scenario is there, when it's present, right? We already talked about the pattern, pi, sigma, pi. That's the basic definition: alternating, double, and single bonds, or pi and sigma bonds, directly alternating. All right. And it's not limited to double bonds, right? I have an alkyne over here, which is 1,3-butadiene, which is also conjugated, right? You can see the pattern here, right? You have pi and you have sigma, and then you have pi. That's the pattern. That's what you're looking for when you are looking to see if conjugation is present. Right? There's another a more advanced definition that we're going to look at in a second. Right? One of the things about a conjugated system is that each carbon has a p orbital on it. And this is what differentiates conjugated systems from non-conjugated systems. And it's what makes them react differently, right? The two carbons here, the two sp, two hybridized carbons, nuclei, are pulling on one another. And so that's going to make the bond here shorter. So those sp2 carbons are attracted to each other's electrons. And that's going to compress the bond distance, the bond length. Right? When that happens, those conjugated systems don't react as just simple alkenes. They actually act as a unit. And we'll talk more about that in the next section. All right, we'll talk more about that in the next section. But those conjugated alkenes act as a unit, and it's a 4-pi system. So this is an example of what we call a 4-pi system. Right, those 4 p orbitals all overlap and make that a 4-pi system. We're going to talk more about that when we talk about cycloaddition. Wow. Right, so if you look at this system right here, and let me upload this handout again for those who just got here. All right, if you look at this system right here, this is not conjugated. You can see the pattern is broken. This is pi, and then you have sigma, sigma, and then pi. That doesn't work. That's not conjugated. Right. The only time a system is conjugated is if you have that criteria of pi, sigma, pi. Right. So let's look at the examples down here. What about the first example? What do you think? Do you see a pattern or the pattern of pi, sigma, pi present here?
Yes.
All right, so you have, again, pi. These are all your pi bonds, and each one of them is separated by a sigma bond. All right, so this is conjugated. This aromatic is also illustrates what we call full conjugation. In order for something to be fully conjugated, it has to have a p orbital on every carbon. It's got to have a p orbital on every carbon. And so when you look here, if you put the p orbitals in on each carbon, you're able to see that, right? Every carbon has a p orbital. So that molecule is what we call fully conjugated. All right, what about here? Yes or no?
No. No.
Right, you have to have a minimum of 2 pi bonds present and alternating pi and sigma bonds in order to be conjugated. This doesn't meet the minimum requirement. Right, got to have 2 pi bonds. You can't a single pi bond by itself cannot be considered conjugated. What about here?
No.
Right, this is pi, sigma, sigma, and then pi. Right, if it's not alternating, it can't be conjugated. Here, yes or no?
Yeah.
All right, it is. You have 2 pi bonds separated by a sigma bond. That's pi, sigma, pi, like so. All right, let's go to this example here. What do you think? This is another aromatic. This is anthracene. What do you think?
Yes.
I agree. If you look all the way around this molecule, it is, you can see that pi sigma pi pattern everywhere. Also, if you look at anthracene, it's another example of something that is fully conjugated. And this is important because when we start covering aromatics, full conjugation is going to be a requirement for aromatics. But you can see here.
Can you repeat what you just said?
About the aromatics?
Yes.
Mm-hmm. So aromatics, this is an example of an aromatic just like the first one. And one of the requirements to be considered aromatic is to be fully conjugated. I'll write it down. So full conjugation is a requirement for aromaticity. You'll see that when we start studying aromatics, that's one of the properties that in order for a molecule to be considered aromatic, it has to be fully conjugated. But if we go back here and put the rest of the p orbitals in, you'll see that this has a p orbital on every carbon. All right, what about this molecule? I'm gonna redraw this down here because I want to make a point with that I'll also reiterate when we get to aromatics. This is cyclopentadiene. Is it conjugated?
Yes.
It is. There's my sigma bond. And it doesn't matter where you find the pattern either. It doesn't have to be in a specific order as long as the pi and sigma bonds are alternating. All right, so that's pi, sigma, and then pi. All right, this is conjugated. And I can even make it fully conjugated. Right, this proton right here has a pKa about 16, not too bad. So if I react this with a strong base like KOH, I can actually turn this into an anion. Let me do this first. Right, I can turn that into an anion by doing proton transfer with the hydroxide. That's negative. Boom, I pick that off and then put those electrons there. And the anion is stabilized by resonance too. So that's why the pKa of that proton is so low, relatively compared to just cyclo pentane, which would have a much higher pKa, somewhere in the 40s or 50s. So what about this? Is this fully conjugated now?
No.
So when you see a charge on a carbon like that, normally that charge resides in a p orbital. So those electrons that are the electrons that are here that may give it that negative charge, they're in a p orbital. So it actually is fully conjugated. Go ahead.
I don't understand. Well, can you explain it more?
Yeah, so when I added the base, right? I made the, let me undo all of this and just keep the, and then I'll redraw with the orbitals. Right, this is where I had what I had. In reality, I'm gonna try to draw it in 3D. It looks like this. So it's all planar. And there's the hydrogen is here, that those electrons are in a p orbital. And the fact that they're in a p orbital and your other pi bonds all have p orbitals on them, that makes that fully conjugated. Right, so that charge, whenever you see a charge on an atom, especially on carbon, it's not, those electrons are not just sitting there. They have to have a home, and so they live in an orbital. It's either going, well, for carbon, there's always going to be a p orbital. Depending on what the atom is, if it has more orbitals in its shell, then it may be a different orbital. But for carbon, if you have a negative charge or even a positive charge, the positive charge on a carbon means that the p orbital is empty. Negative charge means you got a pair of electrons in it. But as always, if carbon is charged, the whatever the cause for that charge, be it a extra electron to make it negative or no electrons to make it positive, it's going to be represented by a p orbital. So I can make cyclopentadiene fully conjugated by reacting it with a base and then pulling off one of those protons. So all the carbons have p orbitals. It was already conjugated to begin with. We saw that. But if I react it with a base, then make that carbon negative, that allylic carbon, make it negative, then I can actually make it fully conjugated. This is and now the cyclopentadienyl anion is actually, it goes from being just a conjugated molecule to being an aromatic. Right, so it's aromatic, and because it's fully conjugated, it meets all the criteria for aromaticity. I'm not going to go into detail about aromaticity because that's a whole section that we're going to study. All right, questions about that? I'm not sure who that was asking, but did that answer your question or clarify it?
Yeah.
Okay. All right, any questions about being able to identify whether or not something is conjugated? This page. All right. And so we talked about this. This is just kind of a recap. It says conjugation occurs when the p orbitals from which pi bonds are formed overlap with one another. So we already talked about that. And that overlap, especially in the middle, pulls everything closer. And so it makes these conjugated systems behave differently than a system that's non-conjugated. So it pulls all the orbitals closer to one another. So conjugated systems have a different chemical behavior than their non-conjugated counterparts. All right. If you, I'm gonna leave this for you. And let's answer this question. Why can't a single bond be conjugated? A single pi bond.
Student that passed out in the class and tried to give us some water.
Oh man.
Yeah.
Is it
Okay.
because it won't have overlapping p orbitals?
It won't have another set of p orbitals to overlap with. That's absolutely correct. Right. That's the whole idea behind conjugation, is that you have these two sets of p orbitals that are overlapping and they really become a system or a unit. If you have them far further apart, non-conjugated, like this one, then that can't happen. Even though you got two pi bonds present, they're not close enough for the orbitals to overlap. I don't know if that point has been made clearly enough, but everything in organic chemistry, as far as reactivity, is all based on orbital overlap and different orbitals overlapping with one another and either sharing electrons or overlapping with a specific orbitals to cause bonds to break. All of that, everything happens based on orbital overlap. All reactions in organic chemistry are going to happen based on orbital overlap. The way you view that, it just depends on which theory of bonding you're looking at, right? Either valence bond theory or molecular orbital theory. But every reaction is going to follow one of those two types of patterns. And then molecular orbital theory, we'll talk about shortly when we talk about cycloaddition, because it's used to explain really higher level types of reactions with complicated like pi systems that react with one another. So we'll talk about that later. All right, let's do number one, because we're going to start discussing this now, addition of HX to conjugated diene. So that's the next two classes, I guess. We'll be working through this, and then wherever we stop, I think we'll have, depending on what the date that's on the syllabus, we'll have time to take another test. And I'm going to grade test 2 today. I apologize for the delay, but I'll have it graded today at some point. All right, let's look at that. What is DBN? Based on what we learned in the last section, tell me what DBN is and what is DMF? Anybody? In the last section, we looked at both of these. We looked at DBN and we should know what DMF is. And to give you a hint, when you see a reaction written like this, normally what's underneath the arrow, those are your conditions, like solvent, temperature, etc. Time, right? So what is DMF? I mean, you don't have to know the name. That would be nice because it was given. It just wasn't given as part of the lecture, but it was given in the elimination video. Actually, given in the substitution video.
It's like dimethylformaldehyde.
Yeah, dimethylformaldehyde. Good. What is it used for? What's it known, like basically used for? Right, it's a solvent, and it's a aprotic solvent. And then DBN, right? If you watch the two elimination videos that I sent, one of them discussed the different bases that are used for E2 elimination. So DBN is a very strong base. Right, so you got a strong base in an aprotic solvent. I don't know if you remember from the chart, from the table we had, but this is the triflate leaving group. Excellent leaving group. What's going to happen? Strong base, aprotic, polar aprotic solvent, and a good leaving group. For E2 reactions, one of the dead giveaways is the presence of a base. Right, that's a dead giveaway. Anytime you see a strong base in the presence of a substrate that contains some leaving group, maybe it's a halogen, maybe it's whatever, that's a dead giveaway for E2. It's one of the main reactants for E2 elimination. All right, so what's going to happen in this example right here? Now, we know it's an E2. Where's the alpha proton?
Where's the what proton? I didn't hear you. I'm sorry.
The alpha proton.
Is it attached to that carbon from the left of the leaving group?
You said to the left, so right here.
Yeah.
Yeah, this is alpha, but it's not acidic. Well, it's not as acidic. This has a pKa probably in the 40s. It's too high for that base. And if you pull it off, it's just not stabilized. So we're going to only be looking at this site right here. So what's the product going to look like? If the reaction is an elimination, what would the product look like? So we see the leaving group, we see the alpha proton. What can we don't have to go through the arrows. We should be able to determine at this point what the product of an elimination, or where the pi bond that's the result of an elimination, where it's going to end up.
Well, if the OTF breaks off,
Mm-hmm.
does it form a carbocation?
Not for E2. There's no intermediates.
Okay, so then it just forms a bond there.
Yeah, remember the E2 is concerted. So the base is going to do proton transfer. The CH bond becomes a pair of electrons used to make a pi bond, and then the leaving group is expelled. right? So the product of that reaction should look like this. Is that right?
I did not think the double bond would go there, but I guess I'm confused.
Okay, where else could it go?
I thought it was gonna go where OTF was, and there'll be something else attached to that. But I think I'm thinking about a different.
Yeah,
I think I'm thinking about a different process.
Yeah, if it's an elimination, all those E2s happen the same way. When we were going through that process of studying the E2 elimination, one of the strategies I gave you was to find the leaving group, find the alpha position, and then that's how you know where your double bonds are going to be. So if this is my alpha proton right here, then the double bond is always going to be between that carbon and the carbon where the leaving group is. So that's why it's here. And then of course there's a whole bunch of other stuff, right? So there's actually I'm gonna draw that on the other side because it's the nitrogen, that's the base. So it's that plus that, right? All of that. But the major product is the diene. So the question is now for the product, is the product a conjugated diene? Does it follow the pattern
Yes.
of alternating? Good, it is. It follows the pattern of alternating sigma and pi bonds. And so knowing that it's a conjugated diene, we're going to talk about I should have put a page in. We're going to talk about two reactions of conjugated dienes. Let me go back because I jumped the gun a little bit. Got 5 minutes, I can do that. All right, so when we talk about conjugated dienes, we're really going to study two reactions. One of them is the cycloaddition. I'll do that one first. So cycloaddition, you take a 4-pi conjugated diene and you react it with a 2-pi. All that 4-pi means is that there are 4p orbitals present. And then 2-pi, there's 2p orbitals present. So 2-pi system, and that can be in a double or triple bond, it doesn't matter. But when you react them together, the reason it's called cycloaddition is because you get a cyclohexene ring in the product. Right? And the way this happens, the mechanism is very simple. And there are other considerations like which orbitals overlap and all that, which we'll talk about later. But overall, the mechanism is just, it's called what we call pericyclic. Right, and then that simply means that the electrons move in only among those 6 atoms that you see, right? So it's called pericyclic. The electrons, like, they move in a circuit. right? So that's one reaction, cycloaddition of that conjugated dienes do. And then the other reaction that they do is addition of HX. Now you've seen this already. So you know that if I take an alkene, this is one of the first reactions we learned in organic 1. I take an alkene and I treat it with, let's say, HCl. What am I going to get from that? Just from the reaction. Let's say,
HCl, the double bond is going to break, and HCl is going to be bonded to that.
so you're going to add HCl across the double bond. Is that right?
Yeah.
Good. All right. So one of my products in this case looks like this, where I have a chlorine here, and then the hydrogen added here. Let me just say that. So there's your HCl added across that double bond. There's another product that you get from this reaction that looks like this, where the chlorine is here. And then the H is here. But we're going to talk about how that happens. All right, this particular reaction, where we add HX to a conjugated diene, this always goes through what we call an allylic cation. So this is always the intermediate, but there's a plus charge here. I'm putting always, and I'm putting emphasis on always, because there's no other intermediate that's going to be present. It's always going to be allylic because it can be stabilized by resonance. This is always the intermediate. To a conjugated diene. All right, so for this particular reaction, there's some things we're going to discuss. And if you watched the video that I sent Friday, then you already have been introduced to it, because it's temperature dependent, and depending on whether it's high temperature or low temperature, that's going to determine which product is favored. So it's either going to be the kinetic or thermodynamic product, but I'm not going to get into because we're already out of time, but we'll talk about it on Wednesday. But just put here that it's temperature dependent. And you got two pathways. One is irreversible and one is reversible. Right, and all that's based on the temperature. All right, questions before we sign off?